All right, guys. So this is the review for exam 4, understanding trigonometry and equations. And we're going to work this review actually a little bit backwards. So let's go to number 10 first, and let's just fill out all this information here. So remember, this exam is given into two pieces. The first piece is a no calculator, kind of fill in the blank piece, and then you'll do that. You'll turn that in, and then you'll get the meat of the exam, which is then you can use your calculator to kind of check your work. And I'll give you a filled out formula sheet. So for this first problem, let's see what we have. So we want to do the reciprocal identities here. And so remember, cosecant of theta is 1 over sine of theta. And secant of theta, it's opposite the letter, so 1 over cosine of theta. And cotan of theta is 1 over tan of theta. So it's just a reciprocal or reciprocals of the big three. And then we have the quotient identities here. And these allow us to rewrite tan and cotan in terms of sines and cosines. So tan of theta is sine of theta over cosine of theta. And then the cotan of theta is a reciprocal of that. So cosine of theta over sine of theta. And then the Pythagorean identities, these are probably the most famous in some sense, at least the first one here. So the first one is what? Cosine squared theta plus sine squared theta is equal to 1. And then the other two identities come from this first one here by dividing both sides out first by cosine squared theta. So if you divide both sides out here by cosine squared theta, so just to put a big quotient here and divide by cosine squared theta, notice what happens. We get a 1 here, so you get 1, and then a plus, and then sine squared over cosine squared is a tan squared theta. And then 1 over cosine squared theta, of course, is a secant squared theta. And then if we change here from cosine squared theta to dividing out both sides by sine squared theta, so notice right here, we get a cosine over sine, which is a cotan, so you get cotan squared theta. And then sine squared over sine squared is the 1, so plus 1. And then equal to 1 over sine squared theta is cosecant squared theta. And those are the trigonometric identities, the reciprocal, the quotient, and the Pythagorean identities that you need to know to be able to do trigonometry well. And then let's get on to the reference table here. And so for the reference table, this I have basically memorized, and we need to know the basic sort of reference angles here in degrees and radians. So in degrees, it's 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And in radians, it's 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, and finally pi over 2 radians. And then what we can do is figure out the sine and the cosine of these angles if we know one thing. All we need to remember basically is the sine is 0, 0, right? Sin gets you nowhere. So it's like square root of 0, square root 1, square root 2, square root 3, then square root 4, so you just count up and then divide each of these by 2. So divided by 2, divided by 2, divided by 2, divided by 2, and divided by 2. And then the cosine of theta is the same as sine, but it's the opposite. So you write square root 4, square root 3. So you just basically count down square root of 2, square root of 1, and square root of 0. So there's this nice little pattern, and they're all divided by 2. So divide by 2, divide by 2, divide by 2. And then, of course, these can be simplified a little bit. Square root of 0 is 0. 0 divided by 2 is 0. Square root of 1 is 1. So 1 over 2. And square root of 4 is 2. So 2 over 2 is 1. So same thing down here. So you get 0, 1/2, and then 1. So you should simplify those, but that's how you fill out the reference table. Now I have the reference table memorized, and then I can use it to fill out the unit circle. So on the unit circle here, I'm just going to do this real quick. So I can fill out the degrees in the first quadrant by simply writing these down. So it goes 0 degrees, 30 degrees, 45 degrees, 60 degrees, and then 90 degrees. And then I can use these angles here to find the other angles. So for example, since I know this is 30, and that's plus 30 is 60, plus 30 is 90, then plus 30 is 120 degrees, 150 degrees. I'm just count by 30s, 180 degrees, 210 degrees, 240 degrees, 270 degrees, 300 degrees, 330 degrees, and then finally 360 degrees. And then because this angle is 45 degrees, I can now count 45. So 45 is 90, plus 45 is 135 degrees, plus 45 is 180, plus 45 is 225, plus 45 is 270, plus 45 is 315, plus another 45 is 360. And so that's how I fill out the degrees in my unit circle. And the same thing works for radians. So for radians, I'm going to focus on my reference table. I can just use the radian line there and fill these out. So it's like 0, pi over 6 radians, pi over 4 radians, pi over 3 radians, and pi over 2 radians. And now I can count with these. So what's the idea? Let's count with pi over 4s first. So pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which is pi, 5 pi over 4, 6 pi over 4, which is 3 pi over 2, 7 pi over 4, and then 8 pi over 4, which is 2 pi. And then I can count in terms of pi over 6s. So it's like 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, and then 11 pi over 6, and then finally 12 pi over 6, which is 2 pi. And then realize some of these reduce. So this one right here is really 2 pi over 3. The 2's cancel basically. This one down here is a 4 pi over 3. Again, the 2's cancel. And finally, this one right here is a 5 pi over 3. And that's how I fill out the unit circle in terms of the reference angles if I have my reference table. Now realize I could also do this by using some of the symmetries of the circle and then counting them out. Now, how do I get the inputs and the outputs on the reference table? Well, that's where the inputs, remember, are defined to be the cosines. And so notice you actually have some nice checking points here. So it might be nice just to fill in checking points like 1, 0 and 0, 1 and -1, 0. I do like these checking points here to kind of fill them out. And then this one 0, -1, kind of keeping me honest in a way, right? So over here, I can check and I have 1. This is that input. And then comes root 3 over 2. So this must be root 3 over 2. And then root 2 over 2. And then that's 1/2. And then comes 0. So this must be 0. So it checks. And then for the outputs, remember that's defined to be the sine of the angle. And so notice you start here with 0. So you have 0, 1/2, root 2 over 2, root 3 over 2. And then finally, we end with 1 and we end with 1. And once you fill out the first quadrant, you get all the other quadrants for free by simply just reflecting across the axes, basically. So let's do the rest of this and see if I can't pull this all up on the screen at the same time. And so there we go. And so I'll get the rest of these by simply reflecting over the y-axis. So the outputs will be the same, but the inputs will all be negative. So this 1/2 will become -1/2. This root 2 over 2 will become negative root 2 over 2. And this root 3 over 2 will become negative root 3 over 2. So you just go to the left, so the inputs now become negative, and the outputs stay exactly the same. So if you have root 3 over 2 here, this stays the same, root 3 over 2. And then we have root 2 over 2, so it becomes root 2 over 2 over here. And this is 1/2, and so that's 1/2. And then, of course, this is 0, so this is still 0. And then we do it again down here, and we just reflect across the x-axis, basically. So everything becomes negative. So, this stays the same, negative root 3 over 2. We'll do the inputs first. It stays the same, -2, root 2 over 2, sorry. And then -1/2. And then, of course, 0 stays 0. And then for the outputs, we have positive 1/2 here, and now it becomes negative 1/2 because they're going down. Positive root 2 over 2 becomes negative root 2 over 2 because you're going down here. That's a 2 there. And then root 3 over 2 becomes negative. Sorry, there's a negative there, root 3 over 2. And then finally, the positive 1 becomes a negative 1. And then we do this one more time. We reflect over the y-axis again. And so all these negative inputs become positive, basically. So negative 1/2 becomes positive 1/2. Negative root 2 over 2 becomes positive root 2 over 2. Negative root 3 over 2 becomes positive root 3 over 2. And of course, you can kind of check it here. Negative 1 become positive 1. But the outputs remain exactly the same. So, this negative root 3 over 2 is still negative root 3 over 2 because, you're in that fourth quadrant there and the outputs are negative. Negative root 2 over 2, still negative root 2 over 2. And finally, negative 1/2 remains negative 1/2. And you can even see here, if you want 0 becomes negative 0, which is just 0. And that's how we fill out the unit circle. All right, so let's go back to the start of this review. And so that's number 1. And so let's take a look at number 1 and see what they want us to do here. So remember, you're supposed to use a separate piece of paper to answer the following problems and then submit it online the day before the exam. So in number 1, it says draw and label the angle 320 degrees in standard position and then convert it to radians. So let's draw the angle first. So we draw the angle here. And this is basically what your XY axis is the idea. Kind of draw it on the unit circle in a way. And so 320 degrees. So you start here and remember, put your arms into it. So you're gonna stop here. 320 is like, well, there's 180, there's 2, kind of stand up, there's 270, and it's not quite to 360, right? So it's somewhere over here in that fourth quadrant. So, you draw the angle here and draw it down here. And so it's in that fourth quadrant, basically, and then just draw the angle around. And that's 320 degrees. And for fun, if you want to, you can put the reference angle on here. So remember 360, and the reference angle is actually 40 degrees. It gets you to that 360 mark. And then let's convert it to radians. And so remember, you have to show your unit. So you have 320 degrees. And the idea is you want to multiply by degrees on bottom and then radians on top. And so in 180 degrees, you have pi radians. So that's a conversion factor. And so that's going to equal, so notice the hundreds places are going to cancel there. So you're going to get 32. I guess it's the tens that are canceling, right? So 32 times pi over 18, right? So the tens places cancel. And geez, I guess those are both even still. In fact, what goes into both of those relatively nicely? I think it's just even. So the 2's cancel, so you get 16 pi over 9, and that's it. Yeah, so 16 pi over 9 radians. And so make sure you get your units on there. And if you want, you can even cancel them off. So that's kind of nice to see like how the degrees cancel, and it leaves you with those radians on top. All right, so let's do this again, but let's do it in terms of radians. So down here on number 2, it says label the angle 7 pi over 3 radians in standard position and then convert to degrees. So let's make our little angle here. So let's draw it. So here's my XY axis. And then my angle is 7 pi over 3. So remember when you see 7 pi over 3, you have to remind yourself that that's really pi over 3. Make that 7 a little bit bigger, 7 times. And so pi over 3, remember, is 60 degrees, like 180 over 3. So 60 degrees, and that's 7 times. So I'm going to really have to kind of think about how this works, right? So it's like here, so 60 degrees 7 times. Man, that's 1, 2, 3, 4, 5, 6, 7. So I'm up in that first quadrant, and you can actually count it off on here if you want to. So it's like, one. So for 60 degrees, it's like 1, 2, 3, 4, 5, 6, 7. So I'm up here in that first quadrant. Actually, if you want to be a little bit better, it's kind of like this. And then I wrap all the way around once and a little bit more. And that's 7 pi over 3, basically 60 degrees taken 7 times. And for fun, if you want to, it doesn't ask this, but you can find the reference angle here if you want. It's pi over 3. radians. All right, now let's convert this to degrees. And so remember, we just write down 7 pi over 3 radians, and we have to show our units. And so divided by or multiplied by something with radians in the bottom here. So here's radians and then degrees on top. Remember, it's pi radians for 180 degrees. So there's our conversion factor. And so notice the pi's are simply going to cancel. And so it's going to be equal to, and 3 goes into 189, 90 times, I guess, right? So not 90 times, but 60 times. Yeah, so 7 times 60, right? Because 3 goes into 18 6 times. And so then that's going to equal 420 degrees. All right. And then feel free to use your calculator to check your work. Remember, you're supposed to do everything by hand, but you can use your calculator to check your work. So there's nothing wrong with doing, 7 times 180 and then dividing it by 3 and seeing that you actually get 420. And the same thing up here, right? I mean, it's not bad to be able to check your work and then do like 320 divided by 180. And you even have a math frac button to kind of help you out. Because I mean, you're going to make mistakes from time to time. And if you have math frac, it tells you what the answer is, 16 over 9. And there's still a pi on there. So 16 divided by 9 times pi. It's been a long day, guys. All right. So there's number 2. And so let's move on here to number 3. And so on this one, what does it say? It says, use the Pythagorean theorem to find the length of the missing side of the right triangle, then find the value of each of the 6 remaining trigonometric, and that should say expressions. It'll say expressions on yours because I'll correct it. That's a lowercase e, so expressions. All right, so those are pretty standard little problems. So the idea is you're just missing side B. And so how do you find side B? Well, again, you use that Pythagorean theorem. We've done this a couple times now. And so the Pythagorean theorem says what? Just says a squared plus b squared is equal to c squared. And so we don't know what our b is. Here's our c and here's our a. And so we just take 6 squared plus b squared, and it's equal to 10 squared. And so that's 36 plus b squared is equal to 100. We'll subtract 36 from both sides and get b squared equal to 64. And then because this is just the side of a right triangle, we can just take the square root of both sides. And so we take the square root of this side and this side, and we only care about the plus part. So b is equal to 8. And so that's equal to 8. Now, armed with this information, along with SOHCAHTOA, we can figure out the value of these remaining 6 trigonometric expressions. So the SO, remember, is the opposite over the hypotenuse, so 6/10. The CA is the adjacent over the hypotenuse, so 8/10. Oops, I keep going in the order that I'd like to go in, but it should be right here. So 8/10. Then finally, the TOA, where's the TOA? Here it is. The TOA tells us that the tan of theta is 6 over 8, the opposite over the adjacent. So here we put 6 over 8. And we can simplify these because they both have a 2 in common on top and bottom. And so that's 3/5. That's equal to 4/5. And that's equal to 3/4. And then below here, I actually wrote them out in terms of their reciprocals. So below them are just the reciprocals. And so this is 5/3. From 4/5, secant theta becomes 5/4. Just flip it, make the reciprocal. And cotangent of theta is 4/3. And so there's the answer for those 6 trigonometric expressions. All right, and so we move on to number 4 now. And so in number 4, we have a little application of these trigonometric expressions. It says to find the distance across a lake, a surveyor took the measurements in the picture below. So here's our picture right here. And the first thing we want to find is the distance from A to B. So we're going to find this distance right here. So we'll give it a name. It doesn't matter what you call it. We'll call it C. And so basically we just want to find C. And so we need an equation for this one. And so for the equation, notice what they give us. They give us the adjacent side to the angle, and we're looking for the hypotenuse. So if we're doing SOHCAHTOA, think for a minute and decide which part are you going to use, the SOHCAHTOA or the TOA. So notice you have the adjacent side, and you want the hypotenuse. So I'll use the CH. So the cosine of the angles, which is 50 degrees, is equal to the adjacent side, which is 640 yards, divided by the hypotenuse, which we call C. And we just basically solve this for C. So I would just clear the denominators here. So multiply everything by C. So I'm going to solve now, and I'll get C cosine of 50 degrees is equal to, and I'll multiply this side by C and get 640. And then divide out both sides by the cosine of 50 degrees. So I'll say cosine of 50. I'm going to drop off that degree marker for a sec here. And so notice these are going to cancel, and I get C equal to 640. That's a bad 4. So 640 divided by cosine of 50 degrees. And that's the exact answer. And most likely I would have you approximate this. So let's approximate this. We can just do to the nearest foot if you guys want to. So on my calculator, make sure you're in degree mode. So hit the mode button. Otherwise, you'll get the wrong answer. So we hit enter. And we'll do 640, and I guess it's the nearest yard we'll do. So divided by cosine of 50, and then hit enter, and out pops 995.6, blah, blah, blah. So let's do 996 yards, 996 yards. And so this side C is approximately 996 yards. All right, so I found the distance from A to B. Now let's just do this again, just for fun. So we want to find a distance from B to C. So that's this distance right here. We'll call this side little a, since the angle over here is capital A. And again, think about which part of SOHCAHTOA you're going to use. And remember, always use the information that's given to you, because if you use any information that you're approximated, then you kind of are going to approximate it again. So it leads to sort of double approximations, which just brings error into your solution, which isn't a huge deal, but if you can eliminate error, you want to. And so from B to C, I would use the TOA, because notice you're looking for this side and they give you the adjacent. So here for my equation, oh, and I'm trying to find A, right? So find A. I would do the tan of 50 degrees. So the tan of 50 is equal to, and this would be the opposite, which is A, divided by the adjacent, which is 640 yards. And now to solve for A, what can we do? We simply multiply both sides by 640. Just clear those denominators again. So multiply 640 over here and 640 there. Now be careful, when you multiply it by 640, the 50 doesn't get multiplied by it. It's stuck inside that tan. So what you do is you put the 640 in front of the tan. So 640 times tan of 50 degrees. And then they'll be equal to, on this side, they'll cancel and just get A. And so then this is approximately, all right, so let's use our calculator again to figure out what it is approximately. So this would be 640. And then tan of 50 degrees. And then hit enter, and it spits out my answer here of 762.7 blah, blah, blah yards. And I'd say round up, right? So 763. So 763 yards is my A. Right, so this is approximately 763 yards. And that's a nice little problem with this SOHCAHTOA in a right triangle. Okay, now moving on to number 5, we get into evaluating these trigonometric expressions. And there are kind of 2 ways to do this. The first way, there's really 3, I guess. You can use your calculator, but that has very little value, of course, just pressing buttons. But the unit circle is kind of nice because it gives you sort of a feeling for where this stuff actually comes from. So we want to compute the exact value of sine of 7 pi over 6. So let's write down sine of 7 pi over 6. And then let's find it. So the way we find in the circle is you find 7 pi over 6. So where's 7 pi over 6 at? There it is right there. You don't really have to have any conceptual knowledge of what 7 pi over 6 actually is. You can see that's 210 degrees though. And then that's going to be equal to, and so remember, by definition, the cosine of the angle is the input value on the circle, and the sine of the angle is the output value. So if you want to find the sine of 7 pi over 6, you find 7 pi over 6, you take the output value. So that's a really nice little problem. Not be worth a ton of points because it's just giving you the answer. You could spice this up a little bit if you want and do something like find the cosecant of 7 pi over 6. That kind of spices it up a little bit. And because you'd have to convert this first, right? So, you need a point or two here for writing this as 1 over sine 7 pi over 6. And then you get a couple points, here by writing down what it is. The sine of 7 pi over 6 is -1/2. And then you could probably get another point out of it by if you multiply it by the reciprocal, it's 1 times -2 over 1, which equals -2. And so that's kind of nice, So, maybe if I asked on the exam, I'd give you a slightly more challenging problem like the cosecant of 7 pi over 6. But it's a nice little a little problem. And conceptually, remember, it kind of tells you, like the input value here is the cosine and the output's the sine. So it's like that height right there is basically 1/2. It's negative because you're going down. And then this length right here is basically √3 over 2, and it's negative because you're going to the left. So it allows you to see that the cosine and sine angle are actually a length of a right triangle. And the positive or negative value of it is given by what quadrant it's in. Okay, let's do this again. But this time, let's use reference angles, because this is a little trickier when you introduce reference angles into it. So this one says use the reference angle to find the exact value of cotan of 4 pi over 3. So there's a lot of little pieces on this one, because first, if you ask me to find the cotan of 4 pi over 3, I'm like, well, I really can't, unless I convert this to sines and cosines. So it's equal to, remember, cosine of 4 pi over 3 divided by sine of 4 pi over 3. So there's sort of step one, convert to sines and cosines. And then the next step is, well, you're supposed to use reference angles. Right now, you don't have a reference angle. So you need to kind of figure out how to rewrite this in terms of 0, pi over 6, pi over 4, pi over 3, or pi over 2. So to do that, what do we need to do? We need to draw the angle 4 pi over 3. So let's draw that angle. So here's my x and y. And I'll draw this angle here, 4 pi over 3. So remember, that's pi over 3 4 times. So I'm thinking to myself, that's like 60 degrees. So it's 1, 2, 3, 4. Okay, so I'm in this quadrant, right? So 1, 2, 3, 4. So it's 4 pi over 3. Down like this. I'm going to label that angle 4 pi over 3. And I need to find the reference angle, because that's what I'm supposed to be using here, reference angle. So the reference angle is the smallest angle you make with the x-axis. There's always two choices, and you take the smaller one. So you can go forward or backwards. Backwards is smaller. And when you go backwards, remember, that's just pi over 3. And you can see that by kind of counting it off. It's like 1, 2, 3. Right? That gives you sort of horizontal, and you go 1 down, pi over 3. And we use all students take calculus to decide whether things are positive or negative. So notice you're in this third quadrant here where only the tan is positive. So each of these, the cosine and sine, are going to be negative. So the cosine is going to be negative cosine of the reference angle. So that's negative cosine of pi over 3. And then divided by the negative sine of the reference angle. So negative sine of pi over 3. Again, lots of nice little pieces here. You can get points, partial credit for all this stuff. And now it's really just kind of look it up. The negatives cancel because negative or negative. So cosine of pi over 3 is what? So here's pi over 3. And then the cosine is 1/2. So we have 1/2 here. And then divided by, and the sine of pi over 3 is right above it. And so that's √3 over 2. And so that's equal to, multiply by the reciprocal. So 1/2 times 2 over √3. The 2's are going to cancel, and you're going to get 1 over √3. And so this is a great problem because why? You can leave that as your answer, but remember, you have an opportunity to earn a bonus point here if you rationalize the denominator. So you multiply top and bottom by √3, You get root 3 on top, and on bottom, root 3 times root 3 is just a 3. All right, now moving on to number 7. What do we have? It says find the exact value of each of the remaining trigonometric expressions. Make sure to include the appropriate diagram. All right, so how are we going to do this? And so we want to basically find the sine of the angle. So sine of theta, and cosine of theta is given to us, but I like to write them all down. So cosine of theta and then tan of theta, along with their reciprocal. So cosecant of theta, secant of theta, and then cotan of theta. And to find these, I'm going to do the same thing we've been doing. All students take calculus. So we'll figure out where the angle lives. And so notice the cosine of the angle is negative, so it can't live here and here. So you have 2 choices now, the second or third quadrant. And it tells you theta is in quadrant 2. So when we draw our theta, here's our theta here in quadrant 2. And you see, you get this little right triangle. I like to color code it. It's kind of nice. And we can use our old friend SOHCAHTOA here. So SOHCAHTOA. And so to find the different sides, remember, the cosine is the ka. And so this is the adjacent over the hypotenuse. So the hypotenuse is 17. Again, I can just kind of color code this. And then the adjacent, that's where the negative sign comes from. It's -8. And then we're missing the opposite side, which is b, but we can just use the Pythagorean theorem to find that. So remember, the Pythagorean theorem just says a squared plus b squared equals c squared. It's really kind of just to plug along and kind of chug to solve it. And so our a was -8, so you have -8 squared. B we don't know, so we just write plus b squared is equal to 17 squared. And so you get 64 plus b squared is equal to, now I don't know what 17 squared is, so I'll probably need a calculator to do my squares. And they usually tell you, so some basic arithmetic, just use your reason. If it's within reason, like, I don't know, 17 squared, so I think that's fine. But if it's 5 times 5, of course, hopefully you're not reaching for a calculator. So I think it said 289. Didn't really pay much attention. Yeah, 289. And then we're going to subtract 64 from both sides. So again, I don't really mind if you kind of just do a little step here and there. And so b squared is equal to 225. I think that's what it said. And then 225, now the question is that a perfect square? So let's just check that out. So the second square root, I think it probably is, right? Usually I try the second answer and you'll see that, yeah, it is. It's actually 15. So b, square root both sides. And we do want it to be positive because you're going up. So b is equal to 15. And so right here, put b equals 15. And so now I'm ready to figure out these different trigonometric expressions. So it's the opposite over the hypotenuse. So it's equal to 15 over 17. The cosine is the ka, which is equal to the adjacent over the hypotenuse. So here's the adjacent over 17, which notice it matches up with what we wanted it to, because you have that one to begin with, right? -8 over 17, but it's nice to check. And then the TOA tells us what the tan is going to be equal to. It's the opposite over the adjacent. So 15 over -8. And the rest of these we get for free because they're just reciprocal. So the reciprocal of 15 over 17 is 17 over 15. It's reciprocal of the sine of theta. The secant theta is reciprocal of the cosine of theta. So it's -17 over 8. And finally, the cotan theta is just reciprocal of tan theta. So it's -8 over 15. And we're all done. All right, moving on to number 8. And so in number 8, we're going to verify some trig identities. So I always enjoy the trig identities. I think they're kind of challenging to verify these things. So let's take a look at the first one. And let's make sure we understand the idea. The idea is that this is a true statement for any value of theta. So any number you plug in for theta, you get the same thing on the left and the right. And to verify it, what you do is you just start with one side. And I always tell you guys you should start with the left because that's how I plan for you to do the problem. So you start with the left-hand side. So you always have to copy it down. So 1 minus sine of theta divided by cosine of theta. And you try to turn this into the right-hand side with a string of equalities, often using a little bit of algebra, and then those identities that we went through at the beginning of this review. So using either the reciprocal, the quotient, or the Pythagorean identity. So this one, we can first just kind of pull apart by giving the cosine of theta to each of these. So that's just a little algebra. So it's like, that's the same thing as 1 over cosine theta minus sine theta over cosine theta. And now we got it. We got the right-hand side basically, right? So it's like secant theta, that's that. So 1 over cosine theta is secant theta. So we basically just replace this with the secant theta. And this is tan of theta. And so minus tan of theta. And so notice, and make sure you put the theta in there, what we showed was that the left-hand side, which is here, is definitely equal to the right-hand side, which is there. And so check, identity verified. We can do this again down here. And again, always start with the left-hand side. So make sure you copy it down or you won't get full credit. So tan of theta plus cotan of theta. And somehow I want to create a string of identities or string of equalities, I'm sorry, to make it look just like that. And so I'm going to start out, because when in doubt, what I usually tell you guys is just transform everything to sines and cosines. So I have sine theta over cosine theta, that's a tan of theta. And I can add the cosine theta over sine theta. So I just convert everything to sines and cosines. And then I say, well, I guess I have two fractions, I'm adding them. So this is really just a little bit of algebra. I'm just gonna find a common denominator and bring them together. So it's gonna be equal to, and so on this one, I'm gonna multiply top and bottom by sine theta. So I'm gonna get a sine squared theta divided by a cosine theta sine theta. And then plus, and this one I'll multiply top and bottom by cosine theta. So I have the cosine squared theta divided by, and then down here, I'll have cosine theta sine theta. So I'm just getting a common denominator. But what's nice now is when I bring these together, I get one of my identities on top. So sine squared theta plus cosine squared theta, all divided by cosine theta sine theta. And so that's equal to, by that, my Pythagorean identity, the one that's, the famous one, sine squared theta plus cosine squared theta is the number 1. And so on top, I have a 1 divided by cosine theta times sine theta on the bottom. And I see where I'm going here, guys. So, look at this. You kind of know where you're heading. So remember, secant theta is 1 over cosine theta. So what I can do is I can separate this. This is just a little bit of algebra. So I can separate this as 1 over cosine theta times, and then cosecant of theta, remember, is 1 over sine theta. So it's like, oh, it works. And so that's equal to, and so what is it equal to? Well, 1 over cosine theta is a secant theta. And then times 1 over sine theta is a cosecant theta. And so now I got where I wanted to go. I went from the left to the right, the string of inequalities, I'm sorry, again, it's been a long day. Equalities, okay? And that's what we call verifying a trigonometric identity. All right, moving on to the last of the problems here, right? These are the tough ones, right? Solving trigonometric equations. And this one is just using reference angles. The unit circle is actually pretty easy to do. These are the harder types of problems. So let's use reference angles here to solve each equation, and make sure to draw and label the appropriate angles. So, make the appropriate diagram basically to solve these. All right, so here's how we start. We have our we're gonna just find where our angle is, right? All students take calculus. And we notice that the tan of our angle is negative √3/2. And it's really the sign I care about. It's not positive, it's negative. So since it's negative, it can't live in the first and third quadrant, because in those two quadrants, if you have an angle, tan is positive. So the angle lives in the second or fourth quadrant. I'm going to draw the angle here. You just draw a straight line. And we're going to look then for the reference angle. which if I can get this to work right, turn the wrong button there. And so here's our little reference angle right here. Now, what is that reference angle? Well, to find it, I need a tan of theta. Now, I don't have a tan of theta line, so I need to put that in there. So remember, tan of theta is sine of theta over cosine theta. So 0 over 1 is 0. I'm going to divide these two, but I'm going to come back to that one because it's kind of a pain. Root 2 over 2 or root 2 over 2 is 1. Root 3 over 2 over 1/2, you multiply by the reciprocal, and the 2's cancel, so you just get root 3. And then 1 over 0 is undefined. And then if you come back to this one, you can just work it out on the side if you want to do it the long way. I don't think there's a problem with it. It's not that bad. It just takes a little bit of work. And so, the 2's cancel, you get 1 over root 3. And then the tricky part here is you typically have to find it, rationalize the denominator, basically, right? And so it's root 3 over 3. The computer's getting slow here too, I think. So root 3 over 3. Now, we didn't even need that piece of information. What we have is the root 3 here, which is right there. That gives us the reference angle. We don't really care about the plus or minus when we look for the reference angle. We just care about the absolute value of that, basically. And so that's pi over 3. So pi over 3 and pi over 3. Now, this one's kind of nice because when you look for the angle x, what is x? Well, it's this angle right here. That's the first answer. And so it's, you can count it off for you. It's just think, you go halfway around, that's pi, and then go back pi over 3. So this is really pi minus pi over 3, which if you find a common denominator, it'll be 3 pi over 3 minus pi over 3, which clearly equals 2 pi over 3. And so my angle, my starting angle is 2 pi over 3. And this is one where you don't have to add 2 pi in, because if you add just pi, you get to the next answer. So you can kind of just write this as a singular answer. It's like you start here, if you add pi, you get to the next one, and another pi, the next one. So it's just plus pi n, where n is an element of the integers. And that's all of my answers. Remember, there's an infinite number of them. You have 2 pi over 3 when n is 0, then when n is 1, 2 pi over 3 plus pi, that is 2 pi over 3 plus pi times 2, and so on and so forth. And n can be positive or it can be negative. And you can even check your work, which I do think is nice to do on some of these if you can. So let me move this over just a little bit. I think I can do it right there. All right, so like notice, you turn this on, make sure you're in radian mode for this one. So just to check my work, put myself in radian mode, and then I'm just going to do the tan. And I'm just going to check 2 pi over 3. So 2 second raised 2 is the pi, and then divide by 3. And out comes my answer, which is that strange looking thing right there. And is that negative root 3? I think it might be, but let's just check it. Negative second square root of 3, hit enter, and boom, you got the right answer. One last problem to do, and then we'll be done with this review. So this is kind of the toughie. And so we did one of these in class basically, but the idea is, this is a trigonometric equation because it involves just sines and cosines or tans of angles of x's. But this one, you have to kind of play with a little bit. So the idea is, they have something in common. So what you can do is you can factor it out. And when you factor it out, you introduce multiplication into your equation. And if you have this times that equal to 0, remember either this is 0 or that is 0. So here's the idea. Sine of x is going to be factored out. It'll be something plus something equal to 0. And then what goes here times sine of x is sine of x. Well, that's just a 1. And what goes here times sine of x is a 2 cosine of x. What's 2 cosine? I'm sorry, not of x, but of 2x. So 2x. And so there's the factorization. And now we have this times that is equal to 0. So now we either know sine of x is equal to 0, or we have 1 plus cosine, 1 plus 2 times cosine of 2x is equal to 0. And now remember, this one's really good to go. We're basically trying to get, remember the big idea, we're really trying to get the sine of something equal to a number, or the cosine of something equal to a number, or finally, the tan of something equal to a number. If we can do that, we can usually use our reference table to kind of solve these types of equations, along with the diagram we need to make. All right, so, this one is good. This one has a little bit more of work to do, so it's not too bad. So we just subtract 1 from both sides, and we get 2 cosine of 2x equal to -1, and then divide both sides out by 2. All right, so we'll get rid of this 2 by dividing out both sides by 2, and now we're good to go. We have cosine of 2x equal to -1/2. Okay, so now we can come back here and solve this one. We draw our little diagram, right? All students take calculus. We'll figure out where the angle x lives. And so where does the angle x live? Well, sine of x is equal to 0. So you get to decide, is 0 positive or negative? And mathematically it's neither, but here you get to decide whether you want to make it positive or negative. So I always just tell you guys, keep it positive. So if it's positive, it'd be up here in these 2 quadrants. But if you want 0 to be negative, then you can put it in the bottom 2 quadrants. It's kind of up to you. And then we draw our 2 reference angles. Now, notice when I draw my reference angle, my 2 angles, I'm sorry, they're right there. And then, I'm looking for the reference angle. That's why I was getting ahead of myself there. And so I go over here to look for the reference angle. I'm like, oh, the reference angle is 0. So you can label these 0, but that's kind of a little bit misleading because, no reference angle means you're basically a horizontal line here, right? So let's fix that picture there. So let's just erase some stuff and we'll redraw our angle along the x-axis here. So there are 2 possibilities. And for our reference angle, of course, we'll just put it right on top here, 0 degrees, right? Or 0 radians, I'm sorry. And so now from this, I can read off what x is equal to. So x is equal to, and we only want the answers between 0 and 2 pi, which is great because it makes my life so much simpler. So the idea is we start here and we go up 0. There's the first angle. And then you don't need to add 2 pi to it or 2 pi in, because if you do, you get bigger than 2 pi basically. And so you don't want to add any 2 pi's to it. So then just put a comma. And the second answer goes from here to here, which is just pi, halfway around. And so pi, and again, don't add any 2 pi's to it because, it'll be too big. You just want the answers between 0 and 2 pi. And don't subtract any 2 pi's either from these answers because it'll be too small. So you just get 2 answers here for that one. And then this one over here, it's a little bit tougher because of that 2x really, but we can start off the same way. So all students take calculus. And notice cosine of 2x is equal to -1/2, which means the angle can't live in the 4th or 1st quadrant. So over here, here's where my angle lives. So I'm going to draw my angles. You get 2 possibilities. And each of these angles have reference angles right there, just smallest angles that mix with the x-axis. And then we're going to go to our reference table and find 1/2 on the cosine line. And we see that the reference angles must be pi over 3. So there's pi over 3 for that one and pi over 3 for that one. And now we can write down our answer here. But the tricky part is that's not an x, it's a 2x. So we get 2x equal to, and our first answer goes from there to there. And what angle is that? Well, the idea is go halfway around, which is pi, and then just go back pi over 3, and that tells you the angle. Find a common denominator, so it's like 3 pi over 3 minus pi over 3. And then it's clear it's 2 pi over 3. And so our first answer is 2 pi over 3. Then we actually have to include the 2 pi in on this one, so you can add any full revolution and get back basically where you started. So plus 2 pi in, n is an element of the integers. And then we have another answer over here, 2x is equal to, and the second answer is right there. And to find that answer, the idea is go pi halfway around and add pi over 3. So pi plus pi over 3. And common denominator, so it's 3 pi over 3 plus a pi over 3, which is 4 pi over 3. Oops, I missed a pi there. And so this is equal to 4 pi over 3. And again, you can add any multiple of 2 pi in, and n is positive, you're, what do we do? You're going this way. And if n is negative, you're going the other way. So, n can be any integer basically. So n is an element of the integers. And then, oops, I don't want to circle that. Yeah. So there's my other possible set of answers. Now, I want to solve this for x, right? So to get x by itself, what am I going to do? Well, I use this little trick, divide by 2. Or if you like, multiply everything by a half. That's kind of the trick. It's kind of nice just to multiply everything by a half. Just nice things happen. So when I multiply this by a half, I get back x. When I multiply this by a half, what happens is the 2's cancel. I just get pi over 3. And then plus, if you multiply this by a half, the 2's cancel and I get pi in. And it is still an integer. Over here, the same thing. So I multiply that by a half. And so I get x equal to, multiply this by half. And then the 4 and 2 cancel a little bit. So I get 2 pi over 3. Plus, multiply this by a half. The 2's are going to go away and I get pi in. And again, n is still an integer. And now for my final answer, I can just count these off. And so what I'm going to do is let n be equal to 0. When that happens, this term's going to go away. And so I'm just going to get pi over 3 for my first answer. Then I'll put a comma. And then when n is equal to 1, this is going to become 1 pi. So x is going to equal, so we're just going to simplify this, pi over 3 plus pi times 1, which is pi, which equals pi over 3, find a common denominator, so 3 pi over 3. And of course, that's equal to 4 pi over 3. And so my second answer is 4 pi over 3. And that's basically it for that one. If you let n equal 2, you can do that, but notice this will be too big, plus 2 pi, and you want to stay under 2 pi basically. If n is negative, what will happen is this will be negative, and that'll be too small. It'll be to the left of 0. All right, so over here we do the same thing, x equal to, let n equal 0. And so when n is equal to 0, that whole thing is 0 there, and you just get back 2 pi over 3. So that's nice. And then comma, let n equal 1. And so what happens when n is equal to 1? Well, you have 2 pi over 3 plus pi times 1, which equals, find a common denominator again. So remember, that's pi over 1, so multiply top and bottom by 3. So you get 3 pi over 3, and that's equal to 5 pi over 3. And so my second answer is 5 pi over 3. And if n is equal to 2, you can try it out, but notice it'll be too big. That'll be plus 2 pi, which, again, you want it under pi. And if it is negative, you'll get a negative number out here. So it's like -1. This will be negative pi over 3, basically. And that's too small. You have to stop at 0 here. And you can check your work, which I think is kind of nice. So, let's check our work. So here's a nice way to check your work if you want. So we'll pick one of the answers we found. Sorry there. We'll pick one of the answers we found down here. Like 5 pi over 3 is probably a good one. So let's just plug in 5. Oops, I turned on the calculator. So 5, and then second raised 2, and then divided by 3, and then hit enter. So there's that angle in radians, kind of crazy, right? But then we can use that and plug into our original equation up here. So check this out. I'm going to do sine of second answer in parentheses plus 2 sine of second answer in parentheses for the sine. Oh, there you are. And then cosine, and then here I had to put 2 times my x. So 2 times, and second answer. There we go, in parentheses. Now, if I get out 0, we're good to go. If I don't, well, we don't have to worry about it. All right, so it's equal to 0. And so that's me just checking my work. And so I'm thinking that these are pretty good. Notice there are a couple little patterns here. So, typically if you just have sine or cosine of x equal to a number, usually just get 1 or just get 2 sort of answers. But if you vary x by a constant multiple, like here you have 2x, you typically double your answer. So instead of 2, of course, you get 4. And so there's some nice patterns like that you can take advantage of. Just kind of check your work relatively quickly. All right, guys, I think that is all we have to do on the review. So take care.